Hi everyone. Hope everybody's fine. Everybody's doing good. Good evening to all. Yeah, good evening. Good evening, everyone. I see two new names. One is who was it? Shrey and Chaitya, right? Are you there, Kana?
Yes,
Shrey?
sir.
So are you new?
Yes, sir.
Like,
I'm new to Epsilon.
okay, this is your first chemistry class.
Yes, sir. Yeah.
Okay. 1 second. Yeah, and another new name which I see was someone I saw. Who was that? Okay, I think I missed it. Like there was one more new name I wanted to ask. Like, okay, so Strain, you had other classes, math, physics, or this is your first class overall in Epsilon Academy as such?
This is my first class, sir.
This is your first class. Okay.
Yes, sir.
Okay, cool. Fine, I think we have enough people. We can start. Which school are you from, Strain?
Sir, DAV itself.
Oh, DAV itself.
Yeah.
Okay. Fine. I'm just looking for the new name again, but I'm not able to find. Right. Fine. One last try I gave. Anyways, okay. So let me share my screen and we'll start right away. So this is 11th. Today is what? 24/09. Right. So people, if you can remember last class, what we were seeing, we were talking about secondary bonds, right? So we know what is the difference now between a primary bond in chemistry and a secondary bond, right? So can someone tell me what exactly is the difference between primary and secondary bonds? Yes, what is the difference, people, between primary and secondary bonds? Go on. This is, I don't know how many, this is, I think, some third or fourth time I'm asking the same question, and I guess the same result that I'm not getting any answer. What happened? Okay, under primary bonds, what and all bonds will come under that, under primary bonds?
Sigma bond, sir.
Okay, sigma bond comes under what? Sigma, pi, all these comes under?
Involve the bond, I mean transfer or sharing of electrons.
Okay,
Covalent
so
bond.
yeah. Okay, yeah, covalent bond, right? So basically pi bond, sigma bond, all these things comes under covalent bond, right? So as she was telling, right, here I have transfer of electron happening, that is, say an electron is completely accepted, right, or completely lost, right? In case of an ionic bond, basically that's how I form a cation or an anion, by losing electron or by accepting electron, and thereby I form an electrostatic interaction, and that's what your ionic bond is, right? Same way in case of covalent bond, we go for mutual sharing of electrons, right? We know how exactly is the force of attraction and all that, right? We all studied that. So what happens here, again, last time I'm telling, next time I'm asking, this exact same answer should come if there is a complete rearrangement in the electronic configuration, right? I have an atom. If an atom completely changes its electronic configuration, that comes under a primary bond, right? Say I know I have loss of electron or gain of electron, or say sharing of electron, right? And in case of secondary bonds, it is only partial rearrangement. That means the electron is not completely lost or completely gained or completely shared. It is not exactly leaving the atom, I would say, right? So under this, what or not we saw, can anybody tell me what were the
Dipole ion, van der Waals forces, and hydrogen bonding.
Okay, right? Dipole ion, van der Waals, and at last hydrogen bonding, right? Okay, so I think we discussed this already, but I'll give you a very quick recap of whatever we saw. Dipole means I should have two dipoles, right? Say this is del minus, and again one more molecule having a del plus and a del minus, right? So I know this is what is called as a dipole. Dipole is something which is equal and opposite charges separated by some distance, right? This is equal charge, but the opposite signs, and they are separated by some distance, right? This entire arrangement is what is called as a dipole, right? So from the name itself, I can understand the bonds means interactions. Bonds mean an attractive force, right? Bonds means some kind of attractive force. We already know that, right? So some kind of attractive force will exist between this dipole, and I can easily understand what exactly is happening here. This del negative and this del positive can have an interaction like this, right? Say now this will happen in any, okay, what is the condition for having dipole-dipole interactions, people? What kind of molecules can give dipole-dipole? How do you categorize them? Okay, sir, by looking at the molecule, I can tell, okay, fine, this will show dipole-dipole interaction. Okay, this will not show dipole-dipole interaction. Based on what will you decide that?
That's the same as dipole moment.
Sorry?
Is the same as the dipole moment.
Yeah, we can tell that, yes.
So then it will be based on the difference in electronegativity.
Or in simple words, I can tell that only polar molecules will have dipole-dipole interactions, right? So obviously for a molecule to be polar, there should be difference in electronegativity between the bonding atoms, like say HCl, say HF, H2O, right? So obviously between the bonding atoms, you see chlorine is highly electronegative, hydrogen is not that electronegative. Same goes with fluorine, high electronegative, oxygen highly electronegative, again hydrogen less electronegative, right? So whenever you see there is different, it's not about electronegativity. People see, if I take Cl, that is chlorine, Cl2, this is non-polar, even though it is electronegative. Please understand, there should be difference in electronegativity, right? Only if I have difference in electronegativity, this particular thing will happen, right? So we have already discussed this, right? Again, I'm telling, say, if I have HCl, the electron cloud will be more towards chlorine because chlorine is more electronegative. Thereby, it will induce a partial negative charge on chlorine, and it will induce a partial positive charge on hydrogen because the electron cloud is moving away, right? So this is what is exactly happening in case of any polar molecule for that matter, right? So if I have to make you understand, say if I take the example of HCl molecule, another HCl molecule, and one more important point I forgot, right? So one major difference between primary and secondary bonds is this, how the electronic configuration is changing. There it is a permanent change. Here it is not it's not a permanent and temporary. Here it is, there it is complete, here it is partial. That's the better way of putting it, right? Okay, so now there is one more major difference. Here the bonds are in between two molecules. That's a very important point to note, right? Say if I say a covalent bond or an ionic bond, it will be between two atoms. Is it not? HCl, one bond. Between hydrogen atom and chlorine atom, I have a covalent bond. Between chlorine atom and chlorine, between sodium atom and chlorine atom, I have an ionic bond, right? But when I talk about secondary bonds, all of these, literally all of these, are going to be between two molecules. We have already discussed this. Say if I drink a tumbler of water, right, is it like only one water molecule will be present? Obviously not. I will have millions and billions of water molecules when you have a small tumbler of water, right? How are these water molecules able to be together, right? So if this particular force doesn't exist in nature, right, you will see only individual molecules. Individual, say for example, if I have to take xenon or neon, for example, right, you will see them only, like say if I take a neon bulb, right, you will see that only one neon atom will be there because I will not be able to put them together. So many atoms or molecules, how will they come together? I need to have some kind of attractive force, right? So that particular force is what is being provided by these secondary bonds. And it is not something which is like say mechanically happening. This is how nature works. Okay, this is how nature works. So anyways, so this is a very important point to note, right? Here, all of these things, it is between two molecules. It can be same molecule or different molecule. That doesn't matter, right? But I should have two different compounds if I have to tell, right? Not so two different compounds, two different molecules, between two HCl molecules, between two H2O molecules, or say between HCl molecule and an H2O molecule. I should have two different or two numbers of molecules. That's what I'm trying to say. Right? Two numbers, at least minimum of two numbers. Yeah, tell me.
Sir, what is di like in written?
Oh, here, this is dipole interactions.
Okay, sir.
Okay, this is one dipole, this is another dipole. The interaction or the attractive force between them is what is called as dipole-dipole interactions. Right? So anyways, coming back to this point, taking this example, HCl, right? Say this is one molecule of HCl. There'll be another molecule of HCl will have the same thing, right? Del positive and del negative, right? So now if they are close by, obviously I can have another interaction here that is between this del minus and this del plus. Okay, right? This interaction, what I wrote in dotted line, this is what is my dipole-dipole interaction. Right, but here you see this bond or this bond you take, these are covalent bonds which are connecting atoms, hydrogen atom and chlorine atom, hydrogen atom and chlorine atom. Right? Okay, so that is about what is that? Dipole-dipole interaction. It can happen in any molecule which is having a polar bond. Even one polar bond is sufficient. Say for example, if you take acetone, CH3COCH3, right? CH bond is not that polar. Okay, CC bond is obviously not polar. Electronegativity difference is 0. Right, but this CO bond you see, again, I have only one polar bond here, right? One polar bond here, and that is enough for me to have dipole-dipole interactions. Okay, how will I represent it? This is how I'll represent it. See, right? C double bond O, CH3, CH3. I'll write like this. Okay, C double bond O, CH3, CH3. Now I know because this bond is polar, oxygen is more electronegative, so it will get a negative charge, and this will get a positive charge. This will get a positive charge. This will get a negative charge. Again, you can see that this is my dipole-dipole interaction. Right? So between, if I have a polar molecule, right, definitely, even if I have one polar bond, that is sufficient for me. Okay, even if I have one polar bond, that is sufficient for me to have dipole-dipole interaction. Okay, right, fine. So now I think from the name, second one, that is my dipole ion interaction, is very, very simple. Okay, but before that, we'll see hydrogen bonding. We already started with hydrogen bonding. We almost completed it, right? So if you understand this, then I'll come back to this. And then at last, we'll see the van der Waals forces, right? So fine, let me see how many of you remember, right? For hydrogen bonding to happen, okay, first, I told you hydrogen bonding is a type of hydrogen bonding, which actually comes under one of the, like say, here we saw 4 things, right? Dipole-dipole, dipole ion, van der Waals, hydrogen bonding. Hydrogen bonding is actually a type of any one of these. What is it?
It's dipole-dipole, right?
Yeah, it's actually, I mean, it can be actually both dipole as well as a dipole ion interaction. Then why are we not categorizing hydrogen bonding under dipole-dipole or dipole ion itself? Why are we giving the specific name? Why are we giving it a specific name, people? Hydrogen bonding. It's a, if you tell that it is going to be a dipole-dipole or a dipole ion interaction only, right? Why do we give it a separate name? What is so special about this? Any guesses? Anybody has? You need not be right.
Sir, is it like hydrogen is usually considered to be electronegative, but then under hydrogen bonding, it becomes electropositive?
How? Like in see, you saw so many cases till now, right? Where did you see hydrogen is electronegative? In what case you saw? See, only you can think of only about this thing. When I have a hydride H minus, right? That case I can tell that yes, hydrogen is electron, but not, most of the compounds, right? Most of the compounds you'll see hydrogen is going to act as an electropositive element. That way, or it is going to have a partial positive charge. That is how it is going to be. Right? Okay. Any other guesses anybody has? Why? What is so special about hydrogen bonding that I have to give it a special name, but not categorize them under dipole-dipole or dipole ion itself? I'm just looking for one word, only one word.
Sir, it's not a covalent bond.
Nothing is a covalent bond here. None of them. Dipole, dipole ion, van der Waals, hydrogen bonding. None of them is a covalent bond here. One last chance to anybody, and I'm going to give the answer. Any random guess anybody has. At least it should be a logical guess. Summa don't tell just because I'm asking.
Sir, can you once show that slide where you wrote about
I wrote about.
the types of forces? Yeah, once.
Okay.
Sir, a little more.
Little this side. Okay, so the answer is it's because compared to normal dipole and dipole ion interaction, hydrogen bonding is very strong. Right? So even though it looks like, or it looks like it is a dipole interaction, but compared to all the other dipole and dipole ion interactions, hydrogen bonding is pretty strong when compared to this. Okay, so that's the reason why we give it a separate name that is called as hydrogen bonding. Right? Okay, fine. With this we understood. Why do we have a separate name? What are the conditions for something to show hydrogen bonding? If anybody is taking notes, this and all should come from your mouth just like that. If you're just looking at your notebooks.
Sir, the atom must be highly electronegative.
What atom must be highly electronegative?
An element should be highly electronegative to make bond with hydrogen, so it forms a hydrogen bond.
Okay, that's a good way to put it. So I need to have something called as hydrogen donors. And what are hydrogen donors is nothing but hydrogen atom attached with a highly electronegative element. That's it. This particular molecule, like this electronegative atom, can be only three. What are they?
Oxygen, fluorine, nitrogen.
Right. So if I have a HF bond, or say if I have a HO bond, or if I have a HN bond, all of these bonds can act as hydrogen donor. This is one condition. For
one more condition is there.
Yeah, exactly. One more condition is there. What is the condition?
Sir, the electronegative atom must have some lone pair on it.
Okay, fine. What is the technical word used? Like hydrogen donor? Like, can you use any technical word?
Hydrogen acceptors.
That's it. Right. So for hydrogen bonding to happen, I should have a hydrogen donor. If something is obviously donating, there should be someone to accept it, right? So I need to have hydrogen acceptor also, right? So as Raghav was telling, now the condition is very simple. For anything to be a hydrogen donor, this is the condition. I should have a hydrogen atom attached with a highly electronegative element, and only 3 elements are possible. It's very simple to understand whether I have a hydrogen donor or not. If I have any of this in any molecule, even if one of them is there, that's enough, right? Hydrogen donor capabilities are there. For hydrogen acceptors, I did not have any electronegative atom per se, right? I don't need any electronegative atom. All I need is a lone pair. That's it. If any molecule possesses any one atom which contains a lone pair, right? That is okay. If I have to give you an example, say acetone is again an example, right? Now see, if I have any of these 3 bonds, actually they themselves can act as both hydrogen donors as well as hydrogen acceptors. Why? Because fluorine has a lone pair, 3 lone pairs on fluorine, 2 lone pairs on oxygen, and 1 lone pair on nitrogen. Right? So already lone pairs are present. Right? So if you find any of these 3 bonds, yes, I can tell that they can have both hydrogen donor as well as hydrogen acceptor capabilities because they're satisfying both the conditions, right? But if you look at molecules like acetone, right? See, what kind of H bond you have? You have a CH bond, which should not be considered under this, right? But you see, this oxygen has a lone pair, so this particular thing can act as a hydrogen acceptor. If it has, because it has a lone pair. Right? Say if I take, for example, PH3, for example, this is not a hydrogen donor. No, because there is only pH bond. But since phosphorus has a lone pair, it can be a hydrogen acceptor. Okay, it can be a hydrogen acceptor. I hope everybody is able to get the point, right? What is the difference between a hydrogen donor and a hydrogen acceptor, right? So now a hydrogen bond is basically an attractive force which is existing between this hydrogen donor and hydrogen acceptor. Okay, a hydrogen bond is what? Hydrogen bond is some kind of attractive force which exists between this hydrogen donor and hydrogen acceptor. Okay, we'll take an example, like you'll clearly understand what is this, right? And why I told you it's a dipole-dipole interaction or a dipole-ion interaction also you'll understand, right? From what I'm going to draw or the example which you're going to see. The perfect example I can have is water. Okay, the perfect example I can have is water. Right. So now you see, as I told, since if you look at this molecule, water, right, I obviously have a hydrogen donor capability because I have two OH bonds which can be hydrogen donors. Right. Right. And obviously, this molecule, again, I told you that the oxygen has two lone pairs. So this molecule itself can act as hydrogen acceptor. Right. Now remember that we are talking about secondary bonds. Right, so it should be between two molecules, right? So even though this particular molecule H2O has both hydrogen donor and hydrogen acceptor capabilities, but at that time it can use only one of them, right? Say for example, if this molecule is going to act as hydrogen acceptor, there should be one more H2O molecule that should be acting as hydrogen donor. Or if it is going to act as a donor, the other water molecule should act as acceptor. You cannot have same thing, like say both the things, you cannot show anything. It doesn't make any logic, right? Secondary bonds, whatever be the type of secondary bond, it should be between two molecules, not between atoms.
Sir,
right? Yeah, tell me.
Sir, could you explain hydrogen donor and acceptor again?
Yeah, no, once again, like if you can just complete the interaction, then you'll understand whatever exactly I'm telling, and then we'll go back to this if you don't understand again. Okay. Right. Fine.
Okay,
now, if you look at this, now see, whenever you have a polar bond, obviously this is a polar bond because it is a highly electronegative atom. Obviously, I know that I'm going to have del positive on the less electronegative atom and del negative on the more electronegative atom. Oxygen is more electronegative, so it has a del minus. Right. Now, I can even take another, I'll take another water molecule. Okay. Now, this water molecule again will have the same thing, right? Sorry, del minus and a del plus. Again, this hydrogen also will have a del plus, no doubt about it. Right now, you see, I can have a dipole-dipole interaction now because this is a dipole, right? This is a dipole. I can have a dipole-dipole interaction here, right? But in this particular case, this special dipole-dipole interaction is what is my hydrogen bond. Right now, you see what now? Okay. Fine, we understood that this is going to say in this particular case, this is going to this particular water molecule is donating this hydrogen. Right? Is donating this particular hydrogen, and this hydrogen is accepted by this oxygen. So in this case, this is going to act as a hydrogen acceptor. Right? That is my hydrogen donor. Right? Because you can understand what I'm trying to say. This hydrogen is getting positive charge and that is interacting with this oxygen. So this oxygen is accepting this hydrogen. Right. So this is going to act as hydrogen acceptor and this is going to act as hydrogen donor. Right. Okay. Now you should ask me one question, which I'm expecting a question. What is the question?
Sir, I have another doubt.
Okay, go on.
Sir, even if a molecule does not, the bonding atom does not have a lone pair, so suppose it has dipole-dipole interaction and the bonding atom gets a partial negative charge. So that can also act as an acceptor, right?
Yes, it can. But okay, that's exactly I would say almost you asked the same doubt which I was asking for. Okay. Now the answer to the question is, or what question I wanted you to ask is, sir, fine, I understand hydrogen donors, how this del positive is helping me. Right, and obviously it is going to have this thing. But what is the role of a hydrogen acceptor? Where you didn't explain anything about the lone pair here, right? I told you this is the hydrogen acceptor, but how lone pair is getting utilized here, I didn't tell you. right? Because this is one way of seeing it, right? I would say this is the ionic way of seeing it. This is a ionic way of seeing it. This is because I have a positive charge, I have a negative charge, because that happens only in an ionic bond, right? Now there is a covalent way of seeing it. Okay, so what is the covalent way? It's very simple, people. Now I'm going to use the lone pair. Now same thing only, hydrogen donor, nothing changes. Del negative, del positive, this is fine for me, right? Now this is my hydrogen donor, right? When I go to hydrogen acceptor, obviously I need the lone pair. I don't have to represent this time any del negative or del positive, right? Now these electrons are already negatively charged, lone pairs, right? So now I can show the interaction between this del positive hydrogen and the lone pair on this oxygen, right? So this is where my hydrogen acceptor capability is with respect to lone pair can be explained, right? Only if you look into the covalent character, right? But that is why I'm telling you, we are not exactly, terming them as dipole-dipole interaction, is because this is only one of the way of looking into it. This is a dipole-dipole interaction, right? Perfect dipole-dipole interaction. This is exactly what was happening between a HCl molecule and another HCl molecule, del negative, del positive. Same thing is only happening here, right? But still, I'm not calling it dipole-dipole interaction, is because there is another way of looking into it, right? That is my covalent way that suggests, or I would say this is really more logical than that one, because it is actually very strong, right? It is actually very strong, and if I consider that the lone pairs are the one which are involving in the hydrogen bonding, I can really tell that that's what makes this particular secondary bond a very strong bond compared to other secondary bonds, right? Okay, so this is, I would say, you do only this, you forget this. Okay, this is why I need a lone pair. I think Suprajit, your question is answered. Why lone pairs?
Yes, sir.
Right? Okay. So now that's what is hydrogen bonding, right? The del positive hydrogen coming from the hydrogen donor and lone. I just need to have a lone pair on any of the molecule. In this case, water itself is acting as a hydrogen donor because hydrogen acceptor because I have a lone pair. Right now, I can do the same thing in case of say NH3. Like say I'll take HF molecule for example. Right now, one HF molecule, I'll say FH. This is going to have del positive, and the other HF is going to have del negative. Right now, if I represent the other HF molecule, right now there are 3 lone pairs, as we all know. Now you can show the interaction between this del positive and this lone pair, right? And this is my hydrogen bond again. Right now, in this case, this is my hydrogen donor because whichever is donating del plus, that's my hydrogen donor, and whichever has a lone pair now is a hydrogen acceptor. Okay, right now, why am I spending so much, say time or energy on making you understand this particular concept is because it's fascinating. Okay, now this particular tell me.
Sir, in water molecule, can one molecule bond with 2 other water molecules?
Yes. Definitely possible. See, I have this particular interaction possible. Between the same water molecule, I can have a lone pair here and the del positive here. Again, this can also interact. Right? Now I can have another water molecule like this. Right? Now that is having a lone pair and this is having a del positive. Again, I can have an interaction like this. Right? But what you have to understand is, for one hydrogen bond, right, I need 1 del positive hydrogen, right, and 1 lone pair. This is what is the condition, right? Just like how we say for a covalent bond, I need 2 electrons, right? For I need 1 electron coming from each atom getting shared. Like that, for 1 hydrogen bond, right, I require 1 del positive hydrogen and 1 lone pair. Right. So as many del positive and as many lone pairs I can have, as many hydrogen bonds I can have.
Sir?
Yes. Yeah.
Sir, actually what I meant was in the first water molecule, can another water molecule be attached to the second hydrogen atom?
Oh, you can. Are you saying that the same hydrogen, another oxygen will be attracting?
No,
like
sir,
this?
No, sir. The second one, the other one.
This one?
Yes.
This
sir.
hydrogen? Yeah, absolutely. Why not? This will have a del positive. I can have another water molecule is having a lone pair here. Again, same thing. That is what is explained here. Right? Both the hydrogens are getting shared in this case. Again, both the hydrogens can get shared. It's very simple. Yes, why not?
And sir,
That's
I
not
have
correct.
another doubt.
Yeah.
Sir, this can also happen in compounds without hydrogen, right?
This can also happen in compounds without hydrogen. Yes, it can happen. Logically speaking, yes, it can happen. But why are we not categorizing that into this category? Is because that is not that strong. This interaction is very strong interaction. That is the only special reason why we study this. And more importantly, this is more prominent if I have hydrogen in the molecule. This is very more prominent, and you will see that. That's what I'm about to tell you. Why is it so special? It's because you will see this particular thing happening inside our body. Right? We know DNA looks like this, right? I'm very bad at drawing, guys, but please bear it with me. I'm very bad at this. Okay, but at least I hope it looks like a DNA. Right? Okay. Now this DNA, if you look, right, this is one particular chemical species. Okay, this, or if I can draw another color, right? This particular thing, I have the one strand. I know DNA is double stranded, right? DNA is double stranded, we call it. Okay, now this DNA, this is one strand of DNA, this is another strand of DNA, right? Now how these strands are able to stay together is because of hydrogen, right? Because between this and this, I'm going to have hydrogen bonding. Between this and this, between this and this, okay, I'm going to have hydrogen bonding. This is very special, right? Not only this, you will study in biomolecules, right? You will study in biomolecules chapter in 12th. You will study about what exactly are the organic species which exist inside the body and how it helps in really regulating the metabolism and stuff, right? So in that you'll study about DNA, RNA, you'll study about proteins, right? Chemically, not the biological importance, chemistry wise, what is the structure, how with the structure, how will I be able to explain how that molecule performs that particular action, right? I know proteins are required for building blocks. It is required for growing, right? DNA and RNA is required for, hereditary information, right? Chemically we'll speak how, but looking at the structure, like I can predict, okay, this is going to react like this. Okay, this is how it does this function, right? So for that, the one of the basic elements you have to understand is hydrogen bonding. Okay, right? So there, this hydrogen acceptor, hydrogen donor capabilities, you must really understand for you, if you want to appreciate from a chemist point of view, how a body, how a living system works. Okay, that is why it is so important. It is so prominent. Right? So did I answer your question, Suprajit? Is it fine now?
Sir, actually, can this type of bonding happen in carbon dioxide?
No, it cannot happen, right? First of all, see, carbon dioxide, I can have dipole-dipole interaction. See, look at this. Right? See, I can have a del negative, del positive, right? Del positive, del negative, I can have an interaction here. But this is not hydrogen bonding. No, this is dipole-dipole interaction. Do you get the point?
Okay, sir, got it.
Right, this interaction definitely exists. This is a polar bond, right? So if I have a polar bond, the moment it will come as a dipole-dipole interaction, right? But if a special case of dipole-dipole interaction is this hydrogen bonding, which is very strong. Okay, I hope everybody understands how is it, right? Del positive hydrogen, that is my hydrogen donor, and lone pair on the other water molecule is going to act as hydrogen acceptor. I think it's very simple to understand. Same thing which is happening here also. Del positive hydrogen and the lone pair, whichever is giving the lone pair is my hydrogen acceptor. Right? Fine. Now we already saw this, but I'm again repeating because I went little fast last class. Okay. Now this hydrogen bonding people can be of two types. What are they?
Intermolecular and intramolecular.
Intermolecular and intramolecular. I think from the name itself you can understand. Inter-school competition, intra-school competition, intra-sports meet, inter-sports meet, interstate, intrastate, inter-district, inter-district. So what you have to understand, intra is means I told you that for generally in a secondary bond, I need two molecules, right? Between two molecules, whatever exists is what is my secondary bond. But a special case is my intramolecular, where I require only one molecule, right? But one molecule should have two sites, right? One molecule should have two sites. One site act as hydrogen donor site, and the other side will be a hydrogen acceptor site. Okay, now till now, whatever we saw, all these are intermolecular between two hydrogen molecules, H2O, H2O, between two HF. I need two molecules. This is intermolecular between two molecules. Now here, all I need is only one molecule, intramolecular, right? Now, if I can give you an example, then it's very easily understood. Look at this example. If I take, this is benzene ring, okay? We'll talk about this more. Don't worry, inorganic, but all you have to now understand is a hydrogen bond here, right? Say, for example, if I have a OH bond here, right? And say another OH bond is here. Okay, now I know this hydrogen obviously will have a del positive and this will have a del negative, and this oxygen has a lone pair here. Now you see I can have an interaction between these two. There are two molecules. It's happening in the same molecule between the two OH bonds, right? Now this is what is my intramolecular hydrogen bond. Right, I need only one molecule for this, right? But till now, what you saw, see here, I need two HFs, right? I require two H2Os, right? This is intermolecular. Okay, this is intermolecular. Okay, right? Now, I hope you understand, right? What exactly is intramolecular? Only one molecule is required, but in that molecule should have two sites. One site, obviously, this site is my hydrogen donor site, and this is going to act as a hydrogen acceptor site. Right, I hope you get it. Very simple. Right, now, this intermolecule itself, I'll be able to classify them into two types. Okay, that means between same type of molecules, right? That means H2O, H2O, HF, HF, NH3, NH3, like that, right? Or it can be between two different type of molecules, between two different types of molecules, right? For example, right? I want to dissolve CH3OH in water. Basically, I'm going to dissolve alcohol in water. Okay, now what do you think will happen? Now see, CH3OH, obviously if I have only CH3OH and say CH3OH, can this have hydrogen bond? Yes or no? If I have CH3OH and CH3OH, can it have hydrogen bond?
Yes, sir.
Right, obviously I have a OH bond, I have a lone pair, so obviously I can have some interaction here, del positive and the lone pair. Right, obviously now only we saw if I have H2O, H2O, again, I can have an interaction between one H2O and another H2O. Right, now, excuse me. Right, so now if I want to understand whether a hydrogen bond is possible between CH3OH and H2O, I would say it is possible. Now, you can show it like this. CH3OH. Now see, both of them have both the capabilities. So you can take any random thing. Say you can take CH3OH as hydrogen donor, or H2O as hydrogen acceptor, or say CH3OH as hydrogen acceptor, H2O as hydrogen donor. You can take anything. We'll try to represent both. Okay, right. Now I have CH3OH. For example, if I take this as the del positive and this as the del negative, this is going to act as hydrogen donor. Right, now water can act as hydrogen acceptor. Right, say I can have a lone pair on this oxygen and I can have a hydrogen bond, and this is going to act as hydrogen acceptor. Right, now opposite is also possible. Right, H2O, del positive, del negative, hydrogen donor. Right, and I can have CH3, I'll write like this, OH, CH3. Right, now again I can have an interaction here, and this is going to act as hydrogen acceptor. Right, so all I want you to understand from this particular concept is that hydrogen bonding can happen between same type of molecule, or it can be different. It can be between two different molecules also, two different types of molecules, two different compounds itself. Right? Okay, I hope you get the point. Yes, any questions?
Sir, can't alcohol react with water to form some other compound?
No. They just form miscible liquids. Okay. Now that whether the reaction will happen or not, right? That we'll try to understand in organic chemistry. Okay. When you go to organic chemistry, I'll tell you. Okay, find this. You'll not. I'll tell you. You will be able to predict whether okay, this is just going to dissolve or there's going to any reaction happening. All this will be able to predict. Now for now, we just have to understand that there is no reaction happening. As simple as that. Okay.
Okay, sir.
Right. So now everybody understood what is intramolecular, what is intermolecular. Again, intermolecular can be of two types. What kind of molecules are involving in hydrogen bonding? Right. Now, the last thing about hydrogen bonding I want to speak is the consequence. Right. If I have hydrogen bonding, what is so special? What is going to happen because I have hydrogen bonding? Guys, I think I have to just lock my charger in just a moment. Okay, it's plugged in. Right. So what I want to talk about is the consequence. Because I have hydrogen bonding, what is going to happen? Right. Now, please understand, people. Boiling point, the first this thing, boiling point or melting point is directly proportional to the amount of secondary bonds I have. Right. The boiling point or melting point is directly proportional to the amount of secondary bonds I have. Can anybody elaborate on this particular point? Explain everybody what I'm trying to say. What do you understand from this statement?
Sir, if the number of secondary bond increases, then there's more interaction between the molecules, and hence more energy is required to break the attraction between them. Hence the boiling point and the melting point.
Okay, why do I have to break the interaction?
Sir, because we are boiling it, or like it's melting.
What exactly is happening in boiling?
So the particles are getting far away from each other. They are being separated.
Okay, if the particle moves far away from each other, what will happen?
Sir, the electrostatic force of attraction reduces between the particles.
No. That I understand. What I'm asking is, if the particle, if two molecules try to move away from each other and they keep on moving away, what will happen? What is actually happening there?
Sir, the
So we are
bond is
breaking
breaking.
the secondary bond.
You again come to the same point, because secondary bonds are breaking. So because secondary bonds are breaking, they are trying to move far away. So
Change in state.
That's what I'm expecting. I'm going to have change in state. Is it not, people? Right? Say now, I know if it is a liquid, say for example, this is a liquid, the particles are very close by because they have a very strong force of attraction between them. Right? But when I boil it, when I give some temperature, these are going to move very far away from each other. And this is what is going to bring in my gaseous state. Right? And you have a very entire chapter for us to study gaseous state. Anyway, in any school, they started gaseous state?
No, sir.
No, sir.
No, sir.
Okay, fine. Maybe we'll go slower than them, but we'll have a lot of knowledge by the time when we go there. So don't worry. Anyways, so now I hope you understand. Here the particles are very close by in the liquid state. Right? Why they are very close by? Obviously because their secondary bond, that is between two molecules, say H2O molecule. In between two H2O molecules, there's going to be a lot of force. Now, if I supply some energy, they're going to move far away and far away and far away. At a point of time, this liquid particles will be very far away that they're going to become a gas. Right? So obviously, if the bonds or they say attractive force binding them is very strong, the more and more temperature or more and more energy you have to give for you to break this bond. Right? And that is exactly what is told by the statement. Okay? Boiling point or melting point is directly proportional to the amount of secondary bonds I can have. Right? Obviously, I can tell in other words that it is directly proportional to hydrogen. Right? Because the other things, that is, or if I can just put the strength order. Right? Hydrogen bonding is the strongest. Right? Then comes your dipole ion interaction. Right? Then comes your dipole interaction, and the least or say the weakest of them all is van der Waals. Between like van der Waals is like gravitational force, universal force. Everything has it. Literally everything has it. Okay, we'll speak about it. Don't worry. Okay, right. So now, if I say consider a molecule like say H2O and H2S. Okay, if I consider a molecule like H2O and H2S, now you see generally heavier things will have more boiling point. Is it not? Right? Generally, a molecule is more heavy, right? More weight it has, right? That will have generally more boiling point. Okay, so that's why I can expect that H2O will have high boiling point, right? But what I have to understand is H2O has only dipole-dipole interaction, but water has hydrogen bonding. So H2O will have higher boiling point than H2S, even though H2S is having more molecular mass. Even though more molecular mass means more van der Waals force. Okay, we'll come back to this point. Okay, you can remember this. Van der Waals is directly proportional to the molar mass. Okay, but we'll explain this later when you go to van der Waals forces. Right. So now generally that's why we say more molecular mass means more boiling point because more van der Waals force. Just like that.
Sir?
Yeah.
Sir, HF molecule is more stronger than H2O, right?
HF, very good point. Hold your thought. I'll come back to this after finishing this. Okay, I know what you're going to ask. I'll answer the question. Okay. So, anyways, so the thing is here I have only dipole, and here I have huge amount of van der Waals force. But still, since hydrogen bonding is present in H2O, that is going to have higher boiling point. That means you can understand how strong the hydrogen bonding is, irrespective of the fact that there is more van der Waals force, more dipole ion interaction. Two things are there, but in water only hydrogen bonding is there. But still, it makes up for the higher boiling point. Okay, right? So this is the first consequence. If I have any molecule having hydrogen bonding, and if I have a molecule which doesn't have it, blindly you can say that that molecule which is having hydrogen bonding will have more boiling point ability because the intermolecular forces are going to be stronger. Okay, right. Now coming to Suprajit's question, right? If I consider HF and H2O, right, which will have a stronger hydrogen bond? Is that what you're asking, Kanna? Right?
No, sir.
Or in other words, I know HF bond is stronger in theoretically speaking, but still HF is generally a gas at 25 degrees Celsius, but H2O is a liquid at 25 degrees Celsius. Okay, right? So even though I know HF, like if I talk about the covalent bond, right? If I talk about the covalent bond, HF bond is stronger than OH bond, no doubt about it, because hydrogen is more electronegative and stuff. Right? At least theoretically, that's what we expect. Okay. But in reality, what is going to happen is, let me tell you. Right. See, if I consider HF molecule, I have these lone pairs, right? Between basically, I'm considered two HF molecules. I have a del positive and say I have a lone pair here. Okay. Now, what happens is, since fluorine is so highly electronegative that it is not going to allow this particular lone pair to participate in this hydrogen bonding. Again, I repeat this point. So fluorine is so much electronegative that it is going to restrict this lone pair from involving in the hydrogen bonding. Right? So that is like little like a repulsive effect. Okay, it is going to hold on to its lone pair so strongly that its ability to get involved in the hydrogen bonding is decreased. Right? But that's not the case with water. Right? Water has a lone pair, and this lone pair comparatively, this lone pair is more available for hydrogen bonding than in the case of HF from fluorine, because fluorine is very highly electronegative. It is going to hold on to its lone pair it's going to tightly hold on to its lone pair and not allowing it, or I would say at least reduce its ability to involve in the bonding. Yes, Suprajit, your question answered?
So that's why it's present in gaseous.
Exactly. That's why even though both of them have hydrogen bonding, but HF at 25 degrees Celsius is a gas because of this reason. It's not that strong a hydrogen bond. Okay, but in H2O, it's a very strong hydrogen bond. That's why H2O is a liquid. Same goes with H2S also. H2S is still a gas at 25 degrees Celsius. Okay, because it doesn't have hydrogen bonding. But in this case, they both have hydrogen bonding, but one is a gas, one is a liquid because it has more stronger hydrogen bonding. I'm not talking about the covalent bond here, people. I am not talking about OH bond and FH bond. I am talking about hydrogen bonding in HF, hydrogen bonding in H2O. Hydrogen bonding in H2O is stronger, even though FH bond is stronger than OH bond. That is a different story. That comes under primary bonds. Okay, here talking about hydrogen bond. Hydrogen bond in water, that is H2O, is stronger. That's why it's a liquid. The other one is a gas. Yes, question. Yes.
Sir, could you repeat why H2S does not have hydrogen bonding?
Okay. Can this be a hydrogen donor? Yes or no?
I mean, yeah, it can be, but it will be
No,
lesser.
no. Like, yeah, okay. So basically, this del plus hydrogen we speak, right? There should be one value, basically, some value will be there. Say, for example, I'm giving you some random value, 100. Right? So the amount of charge del plus should be above 100 for it to be considered to be hydrogen bonding. Just because I have a del plus, even though if it's a lesser value, I am not going to consider it as a hydrogen bonding. I will still only consider as a dipole-dipole interaction. Do you get the point? Right? Say now, for example, in this case, the water molecule H del plus maybe is above 100. Right? But here, since the electronegativity difference between the hydrogen and sulfur is not so much, right? Say it's del 1 positive, maybe it is only 80. Obviously, like I'm not giving you any correct numbers. I'm just relatively speaking. If this is 100, definitely this will be 80 for sure. Right? And that value is not sufficient for it enough to be called as hydrogen bonding. I'll still call it as dipole-dipole only. Yes? Okay.
Yes, sir. Got it.
Right. Okay. Good. All nice questions today. Right. Anyways, I hope everybody is able to follow. Right. Just because like only one person is asking doubts, I'm making sure that everybody actually understands whatever is happening here. Okay. So the first consequence of hydrogen bonding is that if I have hydrogen bonding, that will basically if I have hydrogen bonding, the first consequence is boiling point, melting point. Second is the state. Right. Whether it's a liquid or a gas, right, can also be determined whether I have hydrogen bonding or not. Generally, if I have a liquid state, I can say that it is going to have very strong hydrogen bonding. But again, we cannot generalize it like this, but still we can tell. Right? Okay, so 2 consequences over. The third consequence, which I want to concentrate on, is this solubility. Okay, right. Now we already spoke about this particular point, right? So for solubility, I want you to remember one phrase: like dissolves like. Right? That means what? If I have one type of substance, right, that is going to get dissolved only in that type of substance. Right? And what is the type of substance? Type of substance, there are only 2 types, right? One polar, the other one is non-polar. Very simple. Right? So now how do I understand this? If I have a polar solute, right, that will dissolve only in a polar solvent. Polar solute will not dissolve in a non-polar solvent, and vice versa. Right? That's why we say, when I have, say, for example, NaCl, you try to dissolve in water, it will happen. Right? You try to dissolve it in oil, it won't happen. Why? Because NaCl is polar, H2O is also polar. I hope you understand what you mean by polar. I should be some electronegativity difference. Okay, and oil is considered to be non-polar. That's why how much NaCl dissolves in water, it will not that much dissolve in oil, because polar, non-polar, polar only will dissolve. Polar, non-polar will not be dissolving. Right? Same goes with, I can tell about, say, grease. Right? Grease in water obviously will not dissolve, but grease in oil, it will dissolve. Why? Because grease is non-polar, oil is also non-polar, but this is polar. H2O is polar. That's why it doesn't dissolve here. Non-polar will dissolve in non-polar.
Sir?
Yeah.
Sir, is oil an organic compound?
Oil and organic compound? Yes, correct.
Okay, sir.
Even grease is an hydrocarbon.
Yeah. It is. Hydrophobic. That's the perfect word to use. Yes. Right. Okay. Now, why did I tell this? Is this? if I have between the solute and solvent, between solute and solvent, if hydrogen bonding is present, I'm not talking about solute, solvent, not individually solute, individually solvent. When I put them together, when I mix them, the solute and solvent, I mix them together. If between solute and solvent, like how I dissolved CH3OH in water, right? Both of them can act as hydrogen donor, both of them can act as hydrogen acceptor, and I can have some kind of interaction between them, hydrogen bonding. If this happens, if hydrogen bonding is present, right, there will be high solubility. There will be high solubility. Okay, say if I have to explain this to you, how do I explain this? Now, for example, say CH3OH and water, we'll take a pair, right? And we'll take acetone, that is CH3COCH3 with water. Okay, right? Now, both, or another example we'll take CH3CH3 with water, that is ethane. Okay, all of them, I'm going to dissolve them in water, and without even looking at what exactly is happening after mixing, I'll be able to predict whether which will be highly soluble, which will be okay soluble, and which will not be soluble. Now, can you just think and tell me which will not be soluble? For sure, sir, this is not going to be soluble in water among these three.
So ethane and water.
Yes, absolutely, because this is non-polar and this is polar, right? So this is definitely not going to dissolve. Okay, right? That is a straightforward answer. Now we have to choose between these two. Okay, now both of them will dissolve because both of them are polar, right? But which is going to be higher? Where the solubility is going to be higher? Between these two?
So the first one.
First one. Why?
Sir, because in the first one there's oxygen and hydrogen bonding, so the polar like the polarity will be much higher than in case of second one.
Okay, I understand what you're trying to say. Right, that's one way of looking into it. Right, say I can say there I have OH bond, right? That is highly polar, right? I would say when I talk about polarity, right? Polarity of OH bond is greater than CO bond. Here I have a CO bond. See, this is what is the polar bond here. Right, polarity of OH bond is greater than CO bond. So I can tell that, okay, fine, this is going to dissolve more. That is CH3OH will dissolve more because this is more polar, this is less polar, and this is a polar solvent. I hope everyone gets it, right? But another way of looking into it is in CH3OH can form hydrogen bond with water. I'll say I represent it like this. This hydrogen bond can be in such a way that this can be hydrogen donor, this can be hydrogen acceptor, and this can be hydrogen donor, and this can be hydrogen acceptor. Both the things are possible. Okay, I already explained you how this is possible. But if I take CH3, C double bond O, CH3 and H2O, right? Now you see this particular thing can act as only a hydrogen acceptor because it only has a lone pair. It doesn't have any H bond which is attached to highly electronegative atom. Only CH bonds are there. That is not possible. Right? Now this will have a del positive and I can have an interaction here. This is okay. Right? So what do you mean? That means here there are more chances of creation of hydrogen bond because CH3OH can act as both hydrogen acceptor as well as water molecule is capable of doing that. But here you see only hydrogen donor capabilities are there from water. I mean, this can have both, but only hydrogen acceptor capabilities are present in acetone. Right? And that's the reason why this is going to have, say when I compare CH3OH and CH3COCH3, that is my acetone, when I compare the boiling point, CH3OH is more boiling point because it can have hydrogen bonding. Right? It can have hydrogen bonding with itself. It's all about now intermolecular force when I talk about hydrogen bonding. If it is solubility, it is between solute and solvent. Okay, so anyways, CH3COCH3 has less boiling point because it cannot form hydrogen bond with itself, right? And second consequence is that CH3COCH3 is little soluble in water because it can form hydrogen bond with water. And it is going to be less soluble than methanol because it can act only as a hydrogen acceptor. I told 3 very important points. Everybody got this. Can I get a yes from everybody? Yes?
Yes, sir.
No?
Yes, sir.
Yes, sir.
Okay. Only 3 voices I heard. Everybody's okay, Kana? Everybody's fine?
Sir, could you repeat it one more time?
What I'm telling is, first consequence is CH3COCH3 is going to have less boiling point. This is boiling point because no hydrogen bonding. Here, no hydrogen bonding with itself. Obviously, because it has only hydrogen donor capabilities, only hydrogen acceptor capabilities, hydrogen donor capabilities is not there. Now, second consequence is that CH3COCH3 is soluble in water because of hydrogen bonding. Hydrogen bonding between acetone and H2O. Second consequence. Third consequence is CH3COCH3 is having less solubility in H2O because again here I have only hydrogen donor capabilities, only hydrogen acceptor capabilities. It has both hydrogen donor as well as hydrogen acceptor capabilities. These 3 are the points. Any doubts here? Now,
Sir, I have a doubt.
yeah.
Sir, can we say that in saturated compounds,
Hmm.
all the water molecules have formed hydrogen bonding with the solute. So hence no hydrogen bonding can be formed further, and that's why it becomes saturated. Can we say like that?
Yeah, coming. So for now, for you to understand solubility, certain things, why only polar? Okay, first question is why polar molecules will be dissolved only in polar solvent? Why is a non-polar molecule not able to dissolve in a polar solvent? You have to ask that question first, right? Why is it that the nature chooses solubility problems like this? Why nature does it like this? There's a reason to this. Again, a logical explanation to this. Try to understand. Okay, I'll explain you this. Now, see, for me to make a solution first, right? For me to make a solution, right? Obviously, individually, I have a solute. I have a solvent. Now I'm going to mix them together to form a solution. Right? Okay. Now, for this solution to form, there are certain conditions. Right? What condition? See, for you to make a solution, first thing what you have to do is you have to break solute interactions. Right? I have to break first. We have to break the solute because I'll have, say, one solute, another solute. I'll have some interaction. Same goes with the solvent. Solvent. I can have a solvent interaction. I do not want this. I want them to be separate so that I can have solute-solvent interaction. Okay. So 3 things you have to do. One is break solute-solute interaction, break solvent interaction, and third thing is make solute solvent interaction. Obviously, I think it's very logical, right? Solute is separately there, solvent is separately there. If I want them to be tightly dissolved, obviously I need to have solute-solute interaction to get formed, and I don't want solute particles should come far away, solvent particles should come far away, and solute particles should form. I mean, interaction should form. Okay. Now, if I speak in terms of energy, right? If I speak in terms of energy, the same thing. For these 2 processes, energy should be supplied. Right? For these 2 processes, energy should be supplied, obviously, because you're trying to break it. Whenever you want something to move far away, you have to break the interaction. So obviously, for that, you have to supply energy. That's exactly what you're doing in a boiling process. You want to convert liquid into a gas. So you want to increase the distance. You want to break the force. So you supply energy. Same thing is what you're trying to do here. Okay. Right. Now, second thing is, if a solute-solvent interaction is formed, right, obviously this will release energy. Always remember, bond formation, Energy will be released because it is going to become more stable. We already know energy and stability are inversely related. High energy means less stability. Right? So whenever an interaction or an attractive force or a bond is formed, energy will be released. Whatever be, obviously, if it's a proper primary bond, lot of energy will be released. If it's a secondary bond, little less energy will be released. But as long as some kind of bond is formed, some amount of energy is released. That's what you have to understand. And for bond breaking, energy has to be supplied. I think it's very logical to understand. Okay, right. Now what you have to understand is if you want to have high solubility, okay, if you want to have high solubility, the energy released must be greater than the energy supplied. I think again, it's very logical to understand. Okay, I want the energy released to be greater than the energy supplied. Now, this is one way of looking at it. Why is it like this? It's very simple to understand this, right? See, I told you that the energy will be released, right? So the energy released must be so high. How it can be high? If the energy released will be directly proportional to the solute solvent interaction. How much ever strong, I would say the strength of solute solvent interaction. More and more strong the solute and solvent is having an interaction, more and more energy will be released. Right? Now, I can also say that this is directly, energy supplied will be directly proportional to the strength of solute or solvent. Okay, I think again it's very easy to understand, right? If I have a very strong bond, if I have to break them, I have to supply a lot of energy. Right? Okay. Now, what is the favorable condition now? I want this to be less. I want this to be high. That means what? I need solute solvent interaction to be stronger than solute plus the solvent interaction. Only then, obviously, if these two bonds are little weak, I will supply less energy, right? And if this bond formed is very strong, lot of amount of energy is released. And that is when I will have high solubility. Okay, now coming to the point, polar, non-polar. Remember that if I have a polar solute, that will have a very, very strong interaction with the polar solvent because it can be dipole. Right? Dipole is possible, or say hydrogen bonding is possible if I have polar molecules. Right? But if I have non-polar molecules, only van der Waals force is possible. Right? Only van der Waals force is possible if I have non-polar molecules. Right? But non-polar molecule van der Waals interaction is stronger. Okay, that's the reason. Now I think now everything is connected now, right? I need to have a very strong solute solvent interaction so that you will supply, you will get a lot of energy released, and I want the solute solvent interaction to be very small so that I have to supply only less energy, so that overall energy, if I see, overall energy would have been only released, and that's what makes up high solubility. Okay, and the solute solvent interaction will be stronger if I have this to be polar and this to be polar, or this to be non-polar and this to be non-polar. Polar, non-polar, this interaction is not that stronger. So not some amount of energy is, not that much amount of energy is released. Right? Now, certain times you must have seen certain things will not dissolve at room temperature. Right? But if I start heating them, then you will see that it is going to get dissolved. Why? Because you are satisfying this particular component. For this, I have to break. Right? At a normal temperature, it is not breaking. That's why you're supplying more energy in the form of temperature, right? That is why we say temperature and solubility are directly related, right? More temperature means more amount of energy you supply, more easily you can break the bonds, and obviously more the solubility. Okay, right? We will speak about all these points, what we spoke now again in thermodynamics, right? There's something called as solvation energy. Okay, now I can now only tell you, because you have seen so much, you are seeing that some energy is getting released, right? Because I have solute solvent interaction. energy released because of solute solvent interaction, right? Now that energy released is what is called as solvation energy. Okay, and if this solvent is water, right? Now that energy is what is called as hydration energy, because the solvent is water. In general, solvation energy. If the solvent is water, it's called hydration energy. What is solvation energy or hydration energy? The energy released when that particular component gets dissolved. Why am I getting energy? Because I'm going to have solute solvent interaction to be getting formed. Whenever a bond is formed, energy is released, right? And this energy released is obviously directly proportional to the strength of the solute solvent interaction. And obviously more amount of energy will be released and more amount of solubility will be there. Very, very simple to understand. Anybody has any questions?
Sir?
Yeah.
Sir, what are dispersion forces?
Dispersion forces are a type of van der Waals force. I'll come to that point. When we see van der Waals forces, I'll explain you. Okay, it's called London dispersion forces. I'll explain you once we see about van der Waals forces. Okay.
Sir, van der Waals forces are only for gases, right? Or is it van der Waals radius?
No. Van der Waals radii is only for gases. Yes. Van der Waals forces are universal. Solids, liquids, gas, your Bose-Einstein condensates, all. If at all we have a 7th state of matter, everything will have van der Waals force. It's universal.
But it is very weak when compared to hydrogen bonding, right?
Absolutely, no doubt about it. It's the weakest of the forces. It's the weakest of the secondary forces. Hydrogen bonding is the strongest. Okay, so people, now all I wanted to understand is the consequence, right? The consequence is that I can, where is the consequence? Consequence, yeah, right? Consequence, the first consequence is about boiling point, melting point, right? If at all the molecule is capable of forming hydrogen bonding with itself, then it'll have a higher boiling point. If something is not, then it'll have a lesser boiling point. Second thing, you can talk about the states of the molecule. You'll be able to at least predict or expect which molecule will be in liquid state or which molecule will be in gaseous state, and so on and so forth. And at last, solubility. Right? So in between the solute and solvent, if I can have a high, say, hydrogen bonding strength, obviously that is going to release a lot of energy. Right? Now I can explain it to you. Like we already explained it to you. Why is it like this? The strength of the hydrogen bonding with the help of CH3COCH3. Comparing CH3COCH3 and CH3OH, we saw a third consequence is that CH3COCH3 is going to have more solubility because it has more stronger hydrogen bonding than CH3OH will be more soluble because it is going to have more stronger hydrogen bonding than CH3COCH3. But still, CH3COH is soluble because it is going to have hydrogen bonding, but that is a little weak compared to CH3OH, compared to methanol. Okay, right? So these are the very, very important points regarding your hydrogen bonding, right? What is the time? Okay, we have 15 more minutes, so I'll complete the van der Waals force alone. We'll see tomorrow, right? I will just explain you this dipole ion interaction. What is this? We saw dipole, we saw hydrogen bonding, right? Now we'll see what is this dipole ion interaction. I think from the name itself is very simple to understand, right? Okay, before we move on to this, anybody wants to ask me anything? Anybody wants me to repeat anything? Sir, this I didn't understand. Can you please repeat again? Anybody has any kind of queries? Please go on if you have any sort of that things. Okay, I hope everybody is following, everybody is understanding, everybody is fine. Right, now the last topic for the today is dipole ion interaction. Right, now for this, let us take a real life example. Right, now real life example is where, say, I dissolve NaCl in water. Right, NaCl, I'm going to put it in water. Okay, now we'll see what is going to happen. Right, obviously I know that NaCl is going to dissolve in water, no doubt about it, because obviously both of them are polar. Right, okay, now we'll try to understand what makes up. There should, again, this is a solute, right? This is a solvent, right? I need to have some kind of attractive force, right? Right, now that attractive force is what is my dipole ion interaction here. Okay, that attractive force is nothing but the dipole ion interaction. Obviously we understand this is a solute, this is a solvent. For them to completely dissolve, I should have a very strong solute solvent interaction. Right, now that solute solvent interaction in this case is nothing but your dipole ion interaction. Okay, right. Now, what you have to understand is this NaCl, if I dissolve it in water, this is going to get separated into Na plus and Cl minus ions. Now you can ask me why. Right? Why is because there is going to be some amount of energy spent. You are stirring it, right? You are like say some amount of temperature is there, say in the salt, wherever you've taken it from, it will be maybe in a bowl which is little close, right? So temperature is less. But once you take it out and put it in water, right? Say it might be 30 degrees Celsius. So you're basically some energy from atmosphere it is going to absorb, and this is going to become Na plus and Cl minus, right? But this amount of energy being spent is not a worry. Why? Because I'll tell you, right? Because when I have this Na plus and Cl minus, now look at this. If I take them individually, for example, say I take Na plus, right? Now this Na plus, I am going to have some dipole ion. This is an ion, right? Now all I have to take is a dipole. Now you see del plus, del minus, del plus, right? Now this del minus of oxygen and this Na full positive can have a interaction. This is what is my dipole ion interaction between a dipole, which is del positive and del negative, and an ion, cation or anion doesn't matter, some positive charge or negative charge. Right now, this particular interaction which I mentioned is going to be so strong that it is going to compensate for this particular process to happen. This process requires energy, obviously, no doubt about it. Okay, but this energy is compensated by the energy released from this process because the dipole ion interaction. Obviously, whenever interaction is there, energy is released. Okay, so this energy is required. This energy required for this ionization process is compensated by the amount of energy released due to the dipole ion interaction between Na plus and the water molecule. Not only this, even Cl minus will be able to do the same thing. Cl minus and water molecule will have a del negative, del positive. Now I can have an interaction between this del positive and this fully negative charge. Again, a dipole ion interaction. Okay, right? So whenever you see there's an ion and there's a dipole and they're interacting, fully positive charge, partial negative charge. Partial positive charge, fully negative charge. That's exactly is what is happening in both these cases. Right, and obviously now I think you'll be able to understand the strength order: hydrogen bonding, dipole ion, right? Dipole, and at the last is what I have is van der Waals, right? Obviously, since I have dipole only between partial charges, it is going to be weaker than a dipole ion is between a partial charge and a full charge. Cation and anion, obviously stronger, right? That's why dipole interactions are a little weaker. Hydrogen bonding obviously is strong, right? So this is what is about dipole ion interaction, and that we know that NaCl is highly soluble in water is because the amount of energy released because of this interaction is very high. Why? Because this dipole ion interaction is very, very strong. That's the reason why NaCl is highly dissolved in water. It has very high solubility in water. Okay, that's why any salt for that matter, any ionic compound, we saw in the first class of ionic bonding itself that any ionic compound will generally be highly soluble in water. Why? Because once they get dissolved, they will form the cation and anion, and the cation and anion can have dipole ion interaction with water, which is very strong. So a lot of energy is released. That's why they are highly soluble in water. Any kind of ionic compound for that matter. Okay, we'll speak about this particular case in depth again in thermodynamics. Okay, there are two aspects to it. If you think that this is again already in detail, no, it is not. I can still give you information about this process. We'll study in depth in thermodynamics, the energy aspects, or what exactly the energy is called as. We already know it's called solvation energy, but there are still things to look into it. Okay, anybody has any questions regarding dipole ion interaction? Okay, I hope everything is clear, right? So guys, I think we have 10 more minutes. Maybe can I complete van der Waals also? I think I can complete van der Waals, right? I'll just need 5 more minutes, right? Van der Waals, if I complete this chapter is over. Chemical bonding is done. Okay, now van der Waals, I told you it's weakest of the forces. Now why? Because it is going to arise because of temporary polarity. right? We know what is polarity. Polarity is nothing but separation of charges, del positive and del negative, right? This is because of temporary polarity. But all the other things, that is your hydrogen bonding, dipole-dipole interaction, dipole-ion interaction, they come from permanent polarity. Is it not? The polarity is always there in the molecule, right? But you will understand what do I mean by this term temporary polarity. You will understand now what when I give you the proper explanation, right? So in dipole-dipole interaction, hydrogen bonding, and dipole-ion interaction, there is permanent polarity in the molecule. The molecules are completely polar, right? But here, even if I have non-polar molecules, somehow this polarity comes into the picture. But that polarity is not strong enough. It's only a temporary polarity. This happens even for non-polar molecules. That's why I told you it is universal. Whether I have a polar bond, whether it's a polar compound or a non-polar compound, van der Waals force will exist. Because somehow I'm going to have the separation of charges. Somehow I'm going to have this temporary polarity, right? If I can understand how this temporary polarity happens, obviously it is del positive, del negative, del positive of one atom, del negative of another atom, del negative of this atom, del positive of this atom. That's van der Waals force. All I have to understand is how this temporary polarity is getting developed, right? Now we'll take we'll try to understand this. Okay. See, I have two H2, like, okay, forget about H2. We'll just take any one, say for example, I will take helium. Okay, so between helium and helium, see, I'm drawing a dotted line. This is not a bond. This is a secondary bond. Okay, so helium is not polar, right? Helium is just an atom, right? So how is it that so many in a helium balloon, obviously I know thousands of millions of billions of helium atoms are together there. How are they able to be together, right? It's because of van der Waals force, because there is no other explanation I can give here. If the bond is not polar, hydrogen bonding is not possible because even hydrogen is not even there, lone pair is not there, nothing is there. So the only way I can explain this is with the help of your van der Waals force. Okay, right. Now, if I take a helium atom, right, now it will have a nucleus, right, and I will have two electrons are there. Now for now we'll consider only one electron, right? Now say this helium atom also will have, say, one electron. Okay, now I know that this electrons are completely revolving around this nucleus. This electron is completely revolving around the nucleus. Okay, now see, assume the fact that this electron from this position, it moved to this position. Okay, it is moving from here to here. Okay, this electron is moving from this position to this position. Okay, now see, I want you to correlate this with the polar bond we have. Say if I have a HCl bond. Okay, now what is happening here? Initially, say when the bond started forming, say the electron cloud was at the center. Basically, electron cloud is at the center. But now chlorine is more electronegative. This electron cloud is moving towards chlorine, right? So what is common here? Electron movement is the common thing here between this one, right? And between the case which I told you now, what is the common thing? Electron is moving. That's the common thing, right? Since electron is moving, right, there is something happening. What is happening here? In this case, since electron cloud is moving or electron is moving towards chlorine, I have a partial negative charge and hydrogen is having a partial positive charge, right? Or in other words, towards where the electron is going, to the place where electron is going, I am actually inducing a partial negative charge because I am here, something negative comes to me, towards me something comes negative. So I will get a negative charge, partial negative charge, right? And wherever the electron is moving away from, that is in this case, it is moving away from hydrogen, right? So from that place, from say in this place, the electron is moving away. So this place will keep on adding positive charge because something negative is falling away from this. Right now, same thing I will be able to explain here also. The electron is going towards this point, so I can tell that I'm going to have a del negative here, and the electron is moving away from this particular point, so this point will have a partial positive charge. Just exactly, it is moving towards chlorine, so partial negative. It is moving towards this particular point, so partial negative. It is moving away from hydrogen, so partial positive. It is moving away from this point, so partial positive. Right? Now, same thing can happen for this electron also, but assume that say the electron is here now, and it is going to move to this particular place, right? The direction of movement is like this. Okay, it's like this, right? So now what will happen? This will have a partial positive and this will have a partial negative, right? Both of these are hydrogen atoms, not helium atom. This is one helium atom, this is another helium atom, right? Now you see, now I'm going to have, I created the temporary polarity. Now you see a del positive, a del negative interaction, del negative, del positive interaction, and both these are nothing but the van der Waals forces. Okay, now why am I calling this temporary polarity? It's obviously because I know electron moves at the speed of light, right? For me to even, before even realize that this has happened, the electron would have completed, I don't know, some 10,000 rotations or million times rotations are completed, right? But just because it is moving so fast does not deny the fact that this is happening. It is happening for a short moment of time. Between every small point I can have in the orbit, there is this creation of partial positive, partial negative, partial positive, partial negative, and that with another atom like this, I can have an interaction between these two because of the temporary polarity. And this is what is called as your van der Waals force. Okay, now under van der Waals force, I can have different categories, London dispersion forces, those things. So I would say it is really not worth it to go in depth and study what exactly are those, right? If you're still interested, watch some YouTube videos, or say you can understand to even Google, Wikipedia, you just type van der Waals forces. There are so many types of van der Waals forces. Okay, there'll be very minute differences between this London dispersion force and I don't know, something is there, right? There'll be minute differences. If at all you really want to worry about it, yes, you can not worry about it. If you want to know about it, learn it, it's actually a good thing. You go into internet and search. If you don't understand, you particularly ask me, and then I can explain. But it is really not important. Not important. All is important is what is a van der Waals force? How is it existing? How it is universal? Now, how it is universal? Everything in this universe has electron, because everything in this universe is made up of atoms, and every atom has some electrons, right? And every electron in an atom is moving. So if the electron is moving, there'll always be creation of some amount of temporary polarity, and there'll always be van der Waals force. Okay, so between helium, if it is there, definitely anything with your electron is possible. So that's why we say, when I say the atomic mass, or in other words, the proper words, atomic number is directly proportional to the boiling point or melting point, because more is the number of electrons or protons, more will be this temporary polarity created, more will be the intermolecular force of attraction. Obviously, more will be the boiling point, because more and more energy you have to supply for you to break that bond, break that interaction. Okay. Anybody has any questions regarding van der Waals force? Wonderful. Great. This is what I was expecting. Yes, go on.
Sir, here the electron which is revolving, it gains in partial negative charge. And what gains in positive charge?
No. The electron is here initially. When the electron goes from this position to this position, I'm not telling you should not tell that the electron is getting partial positive and partial negative. This point in the orbit gets partial positive and partial negative. Are you able to get the point?
Yes, sir.
Right. Okay. Any other questions anybody has?
Sir, so after completing half per revolution, what will be the charges, sir?
See, like if you think it that way, it will be very confusing, because you just take any two random points. Any two random points you take, and you take the opposite direction moving of electron in the other atom, and then you'll be able to have the van der Waals force. Now, why am I telling you do not think too much? Is because, as I told you, the electron movement is very fast. By the time you say, if you see that from here, if you ask me to go here, yes, it will have, say, partial negative here, partial positive here, partial negative here, partial positive here. But by the time you even realize this, right, the electron would have completed again, it would have been here or here, anywhere, because it's going to move so fast, right? All you have to understand is, because the moment is happening at a particular, say, a nanosecond, this kind of things are created between every possible point, between this and this, between this and this, between this and this is continuously happening, right? So that is why I can say, if at all it is going to happen only one time, this is really not sufficient. right? But this is going to happen between infinite points which are there in this orbit, infinite points in this particular orbit, and somehow this del positive and del negative are going to interact. Okay, is it fine?
Yes, sir. So the partial charge keeps on decreasing as well as increasing within the...
Exactly. It is all, you see, you must fix the point. Then you have to speak about whatever you're speaking now. Okay, fix one point and
Yes,
then you
sir.
speak. That's it. Very simple. Okay, anybody has any other questions? Okay, wonderful. So I think we'll stop with this for today. So with this, your chemical bonding chapter is over. Okay, so guys, do you want me to teach redox reactions? Because even if I teach, I'll be teaching about oxidation numbers, how to calculate the oxidation numbers, how to balance chemical reactions, right? And that's it. Only two things are there, right? So if anybody wants me to, okay, I want to know it from you. You want me to teach or not? We can, or else we can directly go for, I think, gaseous state.
So we'll go for gaseous state.
What happened? Yes, Raghav, go on.
We'll go for gaseous state.
Okay, one vote for gaseous state. What about others? What others think?
So there isn't anything important in redox reaction.
Maybe I will maybe give whatever is important, maybe one class for redox reactions.
That's okay. That's
Yeah, only one class for redox reactions. I will complete 1.5 hours is more than sufficient for me. Like, because you already know it, there's nothing much to see. So one class for redox reactions. After that, we'll go for gaseous state. Okay, fine.
So Sunday will be redox reactions, right?
What do you say?
Sunday will be having redox reaction chapter.
Yeah. Sunday. This Sunday we'll be completing redox reactions. Yes,
Okay.
correct.
Okay, sir.
Right. Any other questions? Any other queries? Okay. Thank you so much, people. We'll meet again on Sunday. I'm ending the class.
Sir, I have a doubt.
Yeah, Raghav. Any others
Sir.
can? Yeah.
Sir, what's the difference between O nitrophenol and P nitrophenol?
Oh, okay. That is. Let me share my screen. 1 second.
So like O nitrophenol comes under intramolecular hydrogen bonding. Whereas
Yeah, correct. Yeah, see, the thing is, this is what is my benzene ring. Okay, so the numbers I'll keep 1, 2, 3, 4, 5, 6. Okay, now I have the 6 carbon atoms are there. Right now, this position 1 and 2 together are what are called as my ortho positions. Right, 1 and 3. This 1 and 3 is what is called as meta. Right, and 1 and 4 is what is called as para. Obviously 1 and 6 will be ortho, 1 and 5 will be meta, 1 and 6 will again 1 and 4 will again be para. That is same, the symmetric this side. Okay, so now what, so if I have to explain you properly, right, so if I put 2 OH groups here, right, now this becomes ortho diphenol. This is not the correct name, but I can understand why ortho comes, because 1 and 2 are occupied. But say if I have OH and say another OH here, this becomes meta diphenol, right? And say another OH, if I put it in the 1 and 4 position, this is my para diphenol. Okay, now as if your question is about your hydrogen bonding, remember only in ortho diphenol, or whenever I have hydrogen or hydrogen acceptor, only in ortho positions, they will be able to capable of going for intramolecular hydrogen.
So
Right?
numbering is our wish.
Numbering is hard to be. You just start from any, but if wherever I have the functional group, I have OH here, you start from here. You cannot start from here. 1, no.
But any OH we can start.
Yeah, you have to start from there. That's it. Okay, right? So only in ortho, because they are close by. Meta and para, the hydrogen acceptor and hydrogen donor are very far away from each other. So the interaction will not be that strong.
Yes, sir. Sir, and my next doubt is about nitrophenol. We are adding
it's very simple. Instead of this OH, you put NO2 here.
Yes, sir. But what does O nitrophenol and P nitrophenol signifies?
Same thing. O means ortho.
Oh,
P means
okay. Okay, sir. I get it. Yes.
Yeah. Okay. Right.
So is
Anything?
S nitrophenol present actually?
Yes, sir.
M.
M
Sorry.
is there. Meta. Correct. O, P, and M. Ortho, para, meta. Okay.
Okay, sir.
Yeah. Any other question?
No, sir.
Right. Any other question, Hamsini, Sailaja? Any other questions you have?
That's all, sir.
Okay. Fine, Kana. Thank you. Thank you so much. We'll meet on Sunday.
Thank you, sir.
Thank you, sir.
Thank you. Thank you.